Thank you very much.
Thank you. So first of all, I would like to introduce the team who have developed this functionality. Nora, Robbie, and Tamás and Ali are on the main team working on the Markush functionality. Szilárd and Tamás had made the integration with JChem base. Tim Dudgeon has created the Instant JChem interface. Erika worked on the improvements in the structure representation, and Chizzy helped us in the conceptual part and in the algorithm creation. We would like to also thank people at Thomson Reuters who have helped us a lot in the past few years, particularly Tim Miller, Steve Hajkowski, Jazz, and Linda. But we have also got many very useful feedbacks from people in the field, and many of them are still here at the moment. And the forum tomorrow will be another place where we would like to discuss how to improve these tools further to make it more suitable for you. Okay, so I will talk about the Markush DARC file format that we have introduced this year, and also about the tools for the enumeration and the storage and searching of Markush structures. And I will also talk a little bit about the challenges that we had to face to bring the Markush DARC format into the system. Okay, so let's see the input parts. So why the Markush DARC format? The Markush DARC format is the format used in the MMS system, the merged Markush service database, which is a collection of patent structures actually hand curated by Thomson Reuters. And Don Walter will have a talk just after me, and he will talk about this database in more detail. We also have a demo database, a small portion of the MMS available as an Instant JChem project for evaluators. Just let us know if you are interested. And tomorrow we will discuss this demo database in more detail. Okay, but if you are not interested in the patent domain, but rather working on the early research side of that drug discovery, then certainly Markush structures are heavily used in the combinatorial chemistry domain as well. We also have some tools in that area as well. So it is possible to actually create Markush structures relating to combinatorial chemistry, either by doing a reagent clipping. So you start off from a reagent library, you add attachment points to the reagents by, for example, a transformation that can be used by a reactor. And then when we've got the attachment points, we can create the Markush structure by assigning the reagents to a scaffold and so on. Another way is R group decomposition, and here we don't start from a reagent library, but we start from a full molecule library. We do an R table first, a decomposition, and then turn this R table into a Markush structure by simply taking the definitions for R1 and R2 and so on. So, okay, now we've got the Markush structures. Let's see what we can do with them. Now we have created an enumeration tool which can either systematically enumerate the full library, or at least to start to enumerate it, or it is possible to select different parts of the Markush structure and only expand those variables. Now for very large Markush structures, very complex Markush structures, the full enumeration is not not really practical, especially those in the patent domain. Those are really complex. They contain 10 to the 30, 50, and so on specific structures. So for those complex structures, a random enumeration can be very useful, and this randomly enumerates structures from the library, making sure that a uniform distribution in the chemical space is created. Okay, we can also calculate the complexity of these Markush structures, so we can say that, okay, this particular Markush structure describes, I don't know, 10 to the 20 specific structures and so on. And during enumeration, we align the structures the same way as was present in the Markush structure, so that it is easy to get the connection between the Markush structure and the enumerated structures. We also color the different R groups by different colors to make it more easier. Okay, and during this enumeration, there are these generic groups, the homology groups, which are very popular in the patent literature, and these describe chemical functional groups, things like alkyl or aromatic ring or heteroaromatic rings and so on. And for the enumeration of these homology groups, we actually use a set of definitions. And this set of definitions is customizable. So if you don't like the structures that we have selected for alkyl, then you can change it on your own. And you can also define new homology groups this way. Okay. By the way, this set of structures we have obtained by automatically searching through a chemistry library and then checking what are the most often occurring alkyl groups in the library, and we just took the top 20 and we use that as the definition here. Okay. In addition to enumeration, we can also register Markush structures in any of our chemical database tools. So, for example, in Instant JChem or JChem cartridge, it is possible to create a Markush table and register Markush structures in it. Then it is possible to search these Markush tables, and basically during this search, it works in a way as we were searching for the enumerated library. But we do not do any actual enumeration during the search operations because of the large complexity of these Markush structures. We could not do that. We do a different method by figuring out the Markush structure as a whole. Okay, what it returns is basically which are those records which contain the query in their Markush libraries. We have both substructure and full structure search, and the full structure search basically answers the question whether my query is a full enumerate of one of the Markush structures in the library. And during the searching, we do a broad translation of homology groups. It means that specific substructures in the query can match to these homology groups in the database, so alkyl, aryl, and so on. Okay, for the visualization of the substructures, it can be tricky. So when we've got a query like that on the top, we can highlight the substructure in the original Markush structure. So, okay, let's see how it fits. Okay, that part is over there. Okay, and then it connects to R20. That must be here, which further connects to R21, which is somewhere there. Yeah, and so on. So it's not very easy to see where are the pieces of this substructure. So we have, for this, we have created a new method of visualization. We call it Markush structure reduction. And this is the reduced result from this heat. And here we expand those variables that, that overlap with this substructure. And here, the result of this, that we have the substructure highlighted in the same way as it was in the query. So it is very easy to see what is going on. Okay, there are many use cases of this technology. We will talk about this in more detail tomorrow. Okay, some challenges that we have faced during the more recently by the interaction of this Markush DARC format. Okay, there were many features that we already had straight at the beginning. So we could handle query structures. So query structures also represent some kind of generaticity. So these features were already there. So we didn't have to bother with them. Okay. The first challenge was the attachment points. The Markush DARC format make heavy use of attachment points. Up to 8 attachment points could be used for an R group. Now, our structure representation was somehow related to the MDL file format, which had a limitation of 2 attachment points to R groups. So that itself was one limitation that we had to address. Another problem was when R groups were embedded into each other. So for example, here is the scaffold. There is the G3 in the scaffold. And the definition of G3 referred to just G4 near to the attachment points. And we had to make a connection between the attachment point of G3 and G4. Oh, by the way, these G groups are basically the same as the R groups, but the Markush DARC system uses the G terminology. Okay, so yeah, this was a problem that how to make the connection between the different levels of these nested R groups and their attachment points. Okay. The Markush DARC system uses a grandparent table for the description of that connection. And first, we have created a temporary solution to represent multiple attachment points because we didn't have the capacity on the Marvin side to do it. So first, we stored these as attachment points, which had various disadvantages. So sometimes the display became crowded, and then when we had to handle these nested R groups, we had to go up into further parents and assign the attachment points there and so on. So it wasn't really working good. So we have decided to create a new representation for attachment points that Markush has shown. And nicely, it also solved the problem of the grandparent relations, because it means that the connection between the grandparent and the grandchildren can be described very easily locally, so we don't need to go up and forth in the representation. Okay. Another challenge was the abbreviations. Markush has nicely shown that those are available in Marvin. In Marvin, there are about 700 built-in shortcuts already, so it was working fine, and even the search could understand those in specific structures. But that's fine. All we had to do is just to synchronize the definitions in Marvin with the definition of the Markush DARC. But the R group attachment points again made some problem here, because the R group attachment points had to be connected to the definition inside the abbreviation, and still it was nice to be able to show the R group attachment points outside when the abbreviation is closed. So with the introduction of these explicit R group attachment points, it was solved also nicely. We can see the R group attachment points outside, and it still connects correctly in the inside. Another challenge was the homology groups, both in the representation and computationally. Basically, for the representation of these, we use pseudoatoms. Now, the Markush DARC system uses these three-letter abbreviations for the homology groups, which are not always very descriptive. So we prefer the long names, but basically both the three-letter codes and the longer names are available. Another complication with homology groups is the extra properties that are usually expressed on them. And for the representation of these, we have created a general atom property framework, which can not only represent these homology groups, but any other atom property. And this development is going to be released soon in the 5.4 version. Okay, there are a few other problems to represent frequency variations. There were the link nodes originally, and we had to introduce repeating units and multipliers and moieties. These were used for the description of stoichiometry in the Markush DARC system as well, and so on. Okay. Another challenge was the position variation bond that Ákos has shown already how to draw and manipulate. So for the representation of that, we had to extend the S group hierarchy with a new type, and now we've got a relocatable multi-center atom. So and the structures are the atoms are highlighted, which relate to the position variation group and so on. But this position variation representation has been also useful in other areas in the structure representation. For example, for the representation of multi-atom charges or coordination compounds. Okay. And basically, all of these improvements not just allowed us this Markush functionality, but also all these improvements delegate into the query features in the JChem system. So many of these features can be used in queries in JChem base against specific Markush specific structures, molecule tables. Not all are available for Markush tables yet. Okay, and what else keep us busy? You will see that tomorrow. Okay, so to sum up, we have in the last 5 or so years, we have created an infrastructure for storing and enumerating and searching Markush structures. And there is a compatible patent database available for the full patent literature by Thomson Reuters. And we use a well thought out chemical representation. And I think it is, on one hand, it is understandable for the chemists and also convenient to work with. And there is continuous development and further improvements in the pipeline. And thank you for your attention. And do we have time for questions?
Actually, yeah, we're running a little late, but yeah, this is of interest, so let's get the questions.
Okay.
I'm curious if this has been looked at as an extension for registering polymers or other kinds of molecules that you could really think of as existing in a Markush structure, but normally people try to say, oh, it's this, and then they define it, but really they don't know what it is, so it's...
Right. So yeah, currently we handle polymers in molecule tables, but polymers features cannot be mixed with Markush features at the moment. But if that is interesting for you, then certainly we can work on that area. We should discuss that.
Couple more questions.
How do we know you're right? What's the benchmark?
Because he's always right.
Okay. What we usually do, that is why we give out that evaluation data set to people. So you can either take that patent data and try with your own queries and even with structures which are mentioned in the patent and so on. Or you can also create your own Markush structures and look how it relates. And these visualization options are also there to help you to see what is there in the Markush structure and if it is found all right. So you can enumerate the Markush structure and search with the enumerated structures back and so on. We regularly do this kind of tests. I just didn't show you the figures.
How you are dealing with the nested R groups and variable point of attachments? There's also some challenging area there.
Yeah, basically, this has caused some problem with the attachment, with the attached data representation of the attachment points. But with the introduction of these explicit R group attachment points, it makes the thing a lot easier because this allows to express the relationship, the parent relationships, to express it locally at the definition level. So this way, it is basically we can throw out a lot of code which we had to put in the system so that to be able to work those cases.
Thank you.